So let's review. E to the x prime is e to the x. I should write, I want you to get into the habit and never forget that something else follows. Times x prime, I don't use it because I don't need it because it's 1. But if it's e to a function prime, it follows the same pattern. Still e to the function and times the function prime. Now, what happens when we have e to the x? Basically, we have to change the base into e to the x. But this is not e. It's anything but e. As I said, 1/2, 1/3, 1/16, 5, 10, 11. So this will be a to the x, but times natural log a. And you can say, why don't you write here natural log e? Okay, I will. But why I don't?
This one?
Exactly. But natural log a is not 1. The same thing when we have a to a function prime. Follows the same pattern. So it's a to the function, of course, times the function prime. But because the base is not e, I have to multiply by natural log a. Otherwise, I wouldn't, because natural log e is 1. So let's apply this in a couple of problems, at least one. I have one that is quite interesting here. Y equals 2 raised to the power 3, which is raised to power x squared. Ooh. So 2 is raised to power 3, and 3 itself is raised to power x squared. And you could say this is awful. No. See, that's why I have my props. Don't even look at that. We need to differentiate 2 to a power, because I need to show the formula. So, no problem. I have 2 to a function. It's 2 to that function times the function prime times natural log 2. So 2 to whatever times whatever prime times natural log 2. Whatever this is, so don't get scared, whatever it is, it's 2 to a function prime. It's 2 to the function times the function prime times natural log 2. Okay, let's uncover it. I only need to copy it right now. 3 to x squared and 3 to x squared. This is carved in stone, this is carved in stone. Now I have to worry about this. So I'll copy 2 raised to 3 raised to x squared. And now, how do I differentiate 3 to a function prime? 3 to a function prime is 3 to that function times the function prime times natural log 3. So don't get confused. I didn't get there yet. One more time. I copy this. 3 to the function prime is 3 to the function times the function prime times natural log 3. Now I have to copy natural log 2, and I have to copy x squared where it belongs. Finally, I need to differentiate this. That's it. So 2 to the third x to x squared times 3 to x squared times 2x times natural log 3 times natural log 2. Not a problem for a test. A problem to understand the sequence of steps, how you should think, just cover it, don't get scared, write the formula step by step. But no, this is not a problem for a test. Just to see how it works. Okay, one more, and then we'll continue. Any questions on this? So this was a problem just to understand the mechanism and apply it several times. Okay, I like this one, for example, x squared e to negative 1 over x. This one I like. This one is useful, way more than the previous one. So I'd like us to carve in stone one more thing. 1 over x prime is negative 1 over x squared. How come? So let's prove it once and for all, and hopefully we'll remember this. This is x to negative 1. When I differentiate, I bring down negative 1. I subtract 1 from the power, and that's it. So that's how I get negative 1 over x squared. Of course, if I put negative here, this will be positive. So negative 1 over x prime will be 1 over x squared. So these are very important concepts, especially later for chapter 5, please. Super important. Same thing here. Super important. So these two. Okay, so we don't have to prove those over and over. Okay, so coming back here, can anyone tell us what to write? How do we start? What rule applies there?
Do we start with product rule?
Yes, the product rule. Very good. So we differentiate x squared. What do we get first here?
So x.
Very good. E to negative 1 over x plus x squared. Remember how we differentiate e to a function, prime. E to that function times the function prime. So I copy e to negative 1 over x. And what did we say right away? What is negative 1 over x prime equal to? This function, yes, I would kindly ask you to simplify and factor. So I will factor out e to negative 1 over x, and I will write 2x plus 1. This is super important. Okay. Yes, any questions for me? Anyone? We are going to jump to section 3.11, hyperbolic functions, because you have a derivatives assessment due before the test. It's 2 pages long, just 10 questions, and it includes this section, and that will be the end of all list of functions we are going to look at. Hyperbolic functions are combinations of exponential functions. So hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, and hyperbolic cosecant. And you can ask, wait a minute, you just said that they are combinations of exponential functions, and we see trig functions here. They are not trig functions. They have some resemblance, but they're not trig functions. Hyperbolic sine is a ratio, hyperbolic cosine is a ratio, and these follow. So they have some properties characteristic to trig functions, but they are not trig functions. So this is e to the x minus e to negative x, and this is e to the x plus e to negative x. And everything else follows. Tangent is this over this, cotangent is this over this, secant is 1 over sine, 1 over cosine, cosecant is 1 over sine. So they do have some characteristics of trig functions, but they're not trig functions. They are simply combinations of exponential functions. Okay, this is hyperbolic sine, this is hyperbolic cosine. And you could say, what's up with this? Didn't we have enough functions? How come they needed something more? Well, there are a lot of applications in real life situations, and I want to show you. I'm going to share my screen right now. I want to show you examples in which nothing else worked, or this was the best option. Oh, I'm logged out. I'm timed out. Oh, thank you very much. So allow me to log myself back in. Maybe I can get around it.
Professor Lee?
Yes, I'm here. Any questions?
Are we going to have to do 3 web assigns before Thursday?
Well, I can extend that if you'd like, but we really have to finish. So I don't have a problem extending that. Okay, so I'm back to here. I was allowed to get back in. I lost you guys. Where are you? Where are you? I lost you. Okay, you're here. Got it. Okay, so I didn't mean that. I meant to show a graph here. Okay, so the ocean waves. So first of all, as you see, hyperbolic sine kind of looks like sine as the graph, not really. Okay, and this is hyperbolic cosine. You can say, oh, it looks like a quadratic function. Not really. It's a sum of 2 exponential functions. And what I wanted to show you is this application. And they simply found out a long time ago, mathematicians came up with a hyperbolic cosine function as being the best in applications of cables or telephone cable or others between different poles. Okay, so this was the best measure of such a function. Based on who knows? I don't know the details, weather, weight, etc., etc. Okay, ocean waves are modeled by hyperbolic functions. This is the I have not visited St. Louis, so but this is the arch, and this is a hyperbolic cosine function. Okay, that's the architect used a hyperbolic cosine function to determine height, distance between the 2 legs, etc., etc. So there are a lot of applications of hyperbolic functions. Okay, their derivatives, very simple. We're not going to look at anything else. I'm happy with the first 3. Very simple. Hyperbolic sine. I know you're going to say, oh, I know. And hyperbolic cosine, even easier, it's not minus, is the hyperbolic sine. And for tangent, same thing, secant, hyperbolic secant squared. And those are their derivatives. So I like to look at a few examples. Let's say, yes, this is a good one. F of t equals hyperbolic. No, I don't want that because I really want, so I'm going to change this to sine. So hyperbolic sine squared, so I'm going to change that. F of t, hyperbolic sine squared of e to t.
Is the derivative of hyperbolic cosine hyperbolic sine?
Yes, there is no sign change. Yes. I want to remove this, so hopefully if you're looking at the notes, you're not getting confused. Okay, so we want to differentiate hyperbolic sine squared of e of t. Okay, let's see what we get. Remember how we start, although this is not a function composition, it's just a function. But remember how we start. We start from the outer function. The outer function is power 2. We bring down 2. Hyperbolic sine of e to t times the inner function prime, which is hyperbolic cosine e to t, times the innermost function prime, which is e to t. Any questions? Any questions? Okay, so should we look at another example? Yes?
So for this one,
Yes.
Good. Yes, go ahead. I thought someone had a question on this first.
no, I thought I did, but I get it. Never mind.
Okay, very good. So here's another. F of x equals hyperbolic tangent of 1 plus e to 2x. So the same thing, we're asked to determine the derivative of this function. So f prime, we have to first differentiate tangent, hyperbolic tangent. We know it's hyperbolic secant squared of the function times the function prime. And now I uncover 1 plus e to 2x, 1 plus e to 2x prime equals. We cannot do anything to that. Let's copy it. And now we know how to differentiate this. 1 prime is 0. E to a function prime is e to the function times the inner function prime. Is that okay? Is that okay?
So all we're doing is just like rewriting it in a different. Well, we're finding the derivative.
We
but
find
the
the
derivative,
the-
not like doing like super complex math. We're just rewriting it in a different.
We're just differentiating it, and you don't have to do anything. The only thing you can is maybe put this in front, but it doesn't matter. That's fine. That's perfect.
Okay, thank you.
Thank you. Do we need other examples, or are we feeling better about this? These are nice, friendly